We start by generating new security keys. To do so, we'll log into AWS Management Console, select Identity and Access Management, select the user that has correct access, and then generate the keys under Security Credentials tab. To configure AWS CLI, we must run configure command. We will copy access key ID. We'll copy the secret. Select the default region and leave the output. By running configure list, we can verify that the settings were taken. Security groups are used to control access to AWS Elastic Compute instances. To create new compute instance, we must first create new security group that will define firewall and network settings. We will create security group by running create security group command with the group name parameter. For simplicity, let's name it GPU SG. Upon running creation command, AWS returns newly created group ID as a confirmation. Now we will allow incoming traffic for ports 22, 2376, 88, 88, and 5000 by running authorized security group ingress command. We will repeat that command for each port. Once complete, we can confirm changes by listing security group details. That is done by running describe security group with the group name as a parameter. And we can see that all of the ports were added and opened. Now we're ready to create VM instance. I will use Docker to simplify the setup. Docker machine create will handle creation. We have to pass parameter to use Amazon EC2 driver. I ran into issues with the latest Docker version, so I will use an older release. The rest of the parameters outline desired region, OS image, security group, instance type, and a name. I will now speed up the video to save some time. By default, instance does not support password authentication, but it's not an issue as the Docker manages private keys for us. We can use Docker machine SSH to remote into the instance. Now that we have running OS, we need to apply latest patches. This is done by apt update and apt upgrade commands. Now that the system is fully updated, we can go ahead and restart it. CUDA is an NVIDIA parallel computing platform. To use GPU, we must install CUDA drivers. We do that by acquiring repository signature key via apt key command. Signature key allows us to verify genuineness of the downloaded packages. Then we add NVIDIA repository to the list of used repositories and run another update. This time we will specify a parameter to exclude recommended packages. This will save a significant amount of space. Upon completion, we will reboot the system yet again. Docker platforms allow integration of third-party plugins. Conveniently, NVIDIA has such plugin. We can download it in a form of Debian package from their GitHub page. Once downloaded, we need to install it using Debian package management utility. Upon installation, we will test it by running NVIDIA SMI command inside of NVIDIA CUDA container. Output should give us GPU type, utilization load, and other metrics. The output shows that our GPU instance has access to half of Grid K520. It is an older model of NVIDIA card with only 3072 CUDA cores, running at 800 MHz and 8 GB of GDDR5. We will have access to 1536 CUDA cores and only 4 GB of RAM as we're running half of that card. But it should be enough for us. Audacity Learning Platform has a great starter package for anyone who wants to learn robot vision. Platform comes with a variety of software. Today we'll be using Jupyter Notebook, which is the web-based Python IDE, integrated development environment. We will use it to write a Python script that will convert all of our images into the desired format. To install Starter Kit, we will once again use Docker. NVIDIA Docker pull command will allow us to download container image, while the Docker run command will create a new container. We also have to make TCP port and disk storage available to a newly created container. That is done using -p and -v switches, respectively. Once container been created, we should be able to access our web-based IDE by navigating to our GPU instance public hostname at port 8888. That is the same port that we were opening during the creation of the security group in the beginning of this video. Now we need to get a training dataset. We will be downloading one from Cognitive Computations Group's website. This image database made available for download free of charge courtesy of University of Illinois. In order for the files to be available to the container, we have to place them into Home Ubuntu Data, which is the folder that we mapped to the container in the previous step. Once we copy the link, we will have to establish second SSH connection to our GPU instance. Then we will use wget command to download the package. The package comes in a tar.jz format. We will need to extract it using tar with the -xvf parameters. Training dataset has all of its images in portable graymap format. Unfortunately, it's not supported by NVIDIA Digits platform that will be used in the next section, so we need to convert it to portable network graphics. Training dataset contains 1500 images. Converting all of them by hand would take a very long time. Luckily, we have Jupyter IDE and some knowledge of Python to complete this task. On a side note, this is my second attempt to capture this recording. As you can see, when I execute the first line of my code, Python kernel piles it up on the previously executed code. We can quickly fix this by restarting the kernel. Let's start. We need to import libraries that will be used to read and write images, as well as a library that will allow us to perform directory operations. First library will be OpenCV. Second will be the OS. Next we will define variable that will store source and destination path. Now we will read all of the images in the source folder into the variable called images and list them to verify that it's not empty. Now that we have our images, we need to create a for loop that will convert images one at a time. We will join path of the source folder with the file name, read the image with the OpenCV library, calculate the destination file name, join it with the destination path, and the write image with the OpenCV into the new location. For loop will repeat the operations for each image. I use print function after each line to debug my code, as well as break operator to ensure that the for loop executes only once. Now that I'm happy with my code, I will comment out print functions and remove break operator. We have a total of 3 folders to convert: training images, test images, and test images scaled. We will run the script for each of those folders. Upon completing the conversion, we must split training images into 2 separate folders containing positive and negative images as per NVIDIA Digits requirements. Folder and file names are not important. Now we will use NVIDIA Docker to download Digits image and start it as a new container. We will also be mapping port 5000 to the host machine to allow the NVIDIA container to communicate to the outside world, as well as provide it with access to home Ubuntu data directory. Once container been created, we should be able to access NVIDIA Digits by navigating to our GPU instance public host name with the port 8888. That's the same port that we opened during the creation of the security group at the beginning of this video. To create new training dataset, we navigate to Datasets tab, select Classification under Image drop-down, and follow Creation Form. First time we navigate within Digits, it will ask us to create a new username. On the form, we must specify image type, size, location of the training parent directory, and dataset name. Upon clicking Create button, Digits will start processing all of the images into internal database. Upon completion of this process, user will be presented with a variety of information regarding the dataset. It will include mean image, list of the positive and negative images, and some other statistics. Now we will create classification model based on AlexNet. We will need to make adjustment to the model by clicking Customize link and give it a name after modifications were made. From this interface we can also visualize the model and see what it's going to look like. I will speed up the video as the training takes quite a long time. Now that the training completed successfully, we're presented with a variety of statistics. We can review learning graph and make appropriate determinations of what needs to be changed before rerunning the learning process to get better results. To demonstrate how simple it is to create additional models, I will create 2 more models on different networks and let them go through the training process. While LeNet is not capable of recognizing complex objects like cars, I will still let it train to show an example of unsuccessful training within the digits application. The training for these 2 models took little under 20 minutes. I will speed up the video to save time. Here's an example how to test your model. I will be testing AlexNet. Open the model, scroll down to the testing area, type in the path to the test image from the testing directory, and click Classify 1. To test with many images, you will need to export text file from previously created dataset and supply it as a list of images for Classify Many function. This concludes this project video. Thank you for watching.